bit in the community and to offer a chance for others to hear directly from the authors. And it's very nice that the authors agreed to give this presentation. So we will have two of the three presentations in the coming weeks, and then a third will be this fall. Hushin Gupta is out of the country for this period of time, and it wasn't very convenient for him to give a presentation in this time period. So with that, let me pass it over to Alberto to explain a little bit more about what these editorials are that he solicited, and then he can introduce our first speaker, Manu Lall. Alberto?
Yes. First of all, thank you very much for organizing this initiative and for inviting me to introduce it. I'm very grateful to you because, I'm now very motivated to do something new for WRR and for our community in general. And I think that this opportunity to give visibility to this editorial initiative is great. And let me explain briefly the idea. And first of all, the new editorial team of Water Resources Research started this term in April 2013, 1 year ago, more or less. And as you know, we got the journal in a very good shape, and the reputation of the journal was already very good thanks to the hard work of the previous editors and thanks to the effort of the community. So we thought what we could do for promoting even more the visibility of WRR contributions, and we had the idea, which is not strictly new, to promote some type of confrontation in WRR, comparison of alternative views on topical research issues in hydrology. I said that this idea is not strictly new because other journals already are publishing debates among topical researchers in their respective community, in their related communities. And for instance, in statistics, they have this opportunity already. And what I think is original in this editorial initiative is that these debates are something more than a comparison of different opinions, because they give the opportunity to the contributors to reply to the other contribution. And let me better explain how it works. Basically, one editor of the journal sets the question and invites relevant people to write a contribution. And of course, these people can invite co-authors, and then they submit a kind of opinion paper. This paper is reviewed by the editor, typically, maybe with the help of an associate editor. And when the review reports are sent back, we also send the other contributions to each contributor. Typically, we seek 3-4 contributors. So we exchange contributions when the review reports are sent back. And then, while we ask the contributors to revise the contribution according to the content of the reviews, we also give the opportunity to write a comment of at most 500 words on the other contributions. So there is a comparison of different views, and also there is the opportunity to see the reply of each contributor to the other views. And then once that we receive the revised contribution, these are published. And I'm pleased to say that this webinar conference is dedicated to the first debate that was just published. And then the community can send comments by writing commentaries on the journal. So this is an opportunity that we give if the community, if some scientist in the community wants to comment on that, on the debates, he can write a commentary. The commentary is not a comment, so it's just a single contribution, and there is no reply by the original author of the paper that is commented. It's just a commentary on the published contribution. So the first debate, the question of the first debate, as you know, because it's already the title of this conference, was the future of hydrological sciences, a common path forward. And common is between parentheses, because of course the word common is provocative. We wanted to invite people that we know have different views on the topical research challenges in hydrology for the future. And therefore, our prediction was that probably the path forward outlined by these authors wouldn't be the same. Of course, we expected fundamental and significant differences. And you know, the question is very general, very broad, because it was our first debate. We wanted to keep a very broad perspective. On the other hand, I think it's an interesting question. I think each one of us has its own view on the challenges for the future of hydrology. And we thought that it would be interesting to see what is the view of three relevant researchers in our area. And also we thought that this question is a bit provocative, but not too much. We didn't want to start with a fight at the first debate, so we thought it was a good compromise. So who are the contributors? The contributors that we invited and kindly accepted, we are very grateful to them for accepting this invitation, because we recognize that it's a bit challenging to write on such an important question, and to write on an important journal like WRR. So the authors are Upmanu Lall, who is presenting his contribution today, and he is a professor at Columbia University, as we all know. And the other two contributions were written by Jeff McDonnell, who invited Kit Bevan to co-author his contribution. And the third contribution was written by Oshin Gupta, and he invited his former PhD student Gray Nearing to co-author his contribution. And I think it is, we thought it is a very good mix of authors, and as I said, basically the motivation for our selection that drove our selection was to seek alternative views. And indeed, I think that the result is very diverse. You will hear from Manu Lall what is his view, so I'm not anticipating anything now. Let me just say that his contribution was very broad, and you will see that Manu took a global perspective, and it's a kind of contribution that focuses on the global problems of hydrology. But as I said, I don't want to anticipate anything at this stage. The contribution by Jeff McDonnell and Kit Bevan look at the catchment scale, and they discussed on the role of new measurement techniques for the future, and in particular for clarifying the difference between celerity and velocity in the formation of the river flow, with particular reference to headwaters. And I think it is a contribution that, as I said, it focuses at the catchment scale, but still it's very broad. And then there is the contribution by Oshin Gupta and Gray Nearing. They focus on data assimilation as a key way forward to extract more information from data. So at the end, we got a very diverse set of contributions, and I think they are complementary. So we all editors were happy with this, and we think it's a good start and a good topic for discussion. And and I say this in a joking way, the only disappointment that we had was that they didn't fight against the opinion of the other contributors. So they took a very kind way of writing their postscriptums and their comment on the other contribution, which a kind approach that we really appreciated a lot. And of course, with a joking tone, I would say that the only thing that is missing in this debate is probably a real confrontation. But it is something that we can promote now with these conferences that Quasi kindly is hosting, and also we hope to get commentaries from the community. So I take this opportunity to invite all the attendants, if they have an idea, to submit a commentary on this debate and on the views that these researcher authors are expressing. Of course, any commentary to WRR papers is peer-reviewed with the usual WRR rigor, but I think it would be really interesting to get other point of view. And I'm fully happy to discuss also privately by email on the opportunity and to give guidelines if someone is interested in writing commentaries. So this is my introduction, and I hope my introduction meets your expectation. Would you like me also to introduce Manu Lall, or are you doing?
Please go ahead. Yes, please,
Okay.
please do that. And I'll just add, Alberto, that I think that if people have more informal reactions or comments, we will share some of that today, but I think we could also look at other additional mechanisms, right, for encouraging a community debate on these topics. So I think there's both the formal WRR presentation as well as then perhaps a less formal, just more kind of a blog debate. But we can talk about that later, how we can do that.
Okay, this is fine. And also, as I said, the contributions are already published, so they are there, and they are open access. So they are there for any information that you may want to take from them. So I'm pleased to introduce Manu Lall now. Manu, you are online, correct?
Yes, I'm on.
Okay, very good. So please, first of all, let me thank you once again for writing such a nice contribution to WRR. We are really grateful to you. And Manu Lall is a professor of engineering in the Department of Earth and Environmental Engineering and Department of Civil Engineering and Engineering Mechanics at Columbia University. You are also, and correct me if I'm wrong, the director of the Columbia Water Center. And basically, besides this affiliation, Manu Lall is an active researcher in the broad field of hydrology. And Manu has a very good knowledge, I would say an excellent knowledge of statistics and statistical hydrology. But at the same time, I think that what mostly impressed me of Manu is its capability to take a very broad approach and to couple statistical concepts with physically based concepts in hydrology. And he's really very effective in making an efficient synthesis of our basic principle and the basic principle that regulates the hydrological cycle. And also I'm pleased to mention that Manu was the leader of many projects that were addressing water problems for people in developing regions, projects that were very successful in bringing a benefit to society in the developing world. And this is something that I think it's worth noting because I think we hydrologists, our task is that of making science for the benefit, for improving our understanding, but also for the benefit of society all over the world with a global approach. So Manu, I'm very pleased to give to you the floor, and I'm sure that you will be able to summarize the essence of your contribution much and much better with respect to me. Please.
Thanks very much, Alberto. Are people able to see the screen?
Yes, I have it.
Okay, wonderful. So I guess I will get started by thanking Rick and Alberto for the invitation to do this. It's not often that you get a platform to basically just mouth off on things you're thinking about would be good for the community. So I think this is an excellent initiative, and I hope that discussion is generated. The title I chose for my contribution, as Alberto was suggesting, focused on taking a global hydrological view. And I put 4 things up there: one water, one world, many climes, and many souls. So I'll try to define those for you first and then try to march through some of the ideas that I would like people to react to and think about. So first, one water. By that, what I mean is that we need to take an integrated view on the planetary water resources, going all the way from ocean, atmosphere to surface and groundwater to storm water and wastewater, because in hydrology these are represented, but perhaps focused more on surface and groundwater and stormwater and wastewater. And I would like us to think in terms of integrating ocean and atmosphere into that story. So that's the first point. The second point is the our world point, which is, again, Alberto alluded to the global aspect of it. And the key thing that I want to bring up there is that from the science side, the minute I bring up ocean and atmosphere, it's clear that those linkages to hydrology make it global. But the specific points that I want to bring up are first, there is a growing realization that local activities related to water, whether these are natural system physical activities or human activities, can have far-field impacts, both on the water and also, for example, with floods, on what happens with the impacts locally can be translated into global impacts on economies and so forth. So keeping those aspects of globalization in mind, the second one that I've listed there is that one of the most remarkable things that has happened is that we have a very rapid knowledge, thought, and technology transfer nowadays as part of the connected world. And this is worth keeping in mind because what it suggests is that if you had a desire to travel the wilds of Mongolia, you might actually have a scientific reason to do so and may have a significant impact in the process. The last point on this slide in the main bullets is on virtual water, which I'm sure many of you have heard of, because people are discussing the embedded water in many products, primarily agricultural, but also other products, and discussing that as a means of looking at smoothing spatial variability and temporal variability in hydrology in terms of its impacts on human societies. But here, what I'm going to do is I'm also going to include a future-looking thing, which is what do we expect based on water availability, changing water availability in different places in the world, as to what that might translate into spatial patterns of human development or land use change, and hence into a feedback into the hydrological system. So summarizing this, the things that are of interest are long-term cumulative effects in a place and across the world, the emergence of space-time patterns across the different things that connect to water, and finally, the planetary regulation. This is essentially looking at climate being regulated by water vapor in a certain sense, and we'll develop that idea as well. So the next point I had was the many climes, and so of course, obligatory to show that we have some classification of the world's climates, and most people are familiar with that, so I'm not going to spend time on it, but these are the typical Köppen classification style of maps of different climate regimes, and we usually talk about hydrology as indexed to one of these things, either in the usual, in the classification sense, or parameterized by a Budayko curve. We have the climate change story, which suggests that these regimes will change as we look into the future, and many people are working on that and are excited about it. But what I wanted to mention was that it's useful to recognize that over the last 5,000 years or longer, we have also seen significant changes in these climate zones. So nature changes and man changes nature, and we need to keep those things in mind if we want to understand what is happening. The last one is, of course, the many souls. We have the growing global population and the growing intensity of resource use, all resources, as this population grows in affluence. So in some metrics, we have the highest performing human population in terms of the living standards, in terms of their intensity of use across the board, but obviously with much inequity as well in those aspects. And what we see is that if we look at the growth out to 2050, it is differential, higher in certain parts of the world. So that poses a very interesting challenge in terms of how we look at what the world of the future might look like. And that's one of the elements I want to build in. So what I did was that compared to the way I wrote the paper, I've sort of inverted the story. And I'm going to put the leading question out first, and then we'll start developing that story out a little bit. So the basic thing that I responded to when I was asked to look at a common path forward for hydrology was what would be a global challenge that would be intellectually interesting, but also would have a very high social relevance. And I think in our field we need that because we often see the rhetoric that water is life and similar statements, but it's not altogether clear that we take that as a unifying thing and try to do something about it. So the question that I pose is, how can we assure a reliable supply of water of appropriate quality for all life around the world by 2050? And some may think that this is a water management question, and indeed it is, but really this is a scientific challenge on how sustainability or resilience or all the other buzzwords that are being thrown together could be unified into a single sharp challenge for us as a field to articulate our importance to the world. And obviously this impacts all the different aspects of human activity. Now, if I parse that further, one way to say this is, from a water perspective, how can we identify which parts of the planet will be habitable and which functions of human activity or of life will they be able to support in a reliable way by 2050? So this clearly brings up the notion that we are looking at A, a future, B, perhaps we recognize that the future is not static, and that in that sense, we are interested in seeing what functionality would exist within that variable future. And within that, one of the things that we are often quite interested in or called upon to answer are floods and droughts or pollution hazards and other things. And the question I put with regard to that as a sub-question to the overall theme is, how will the exposure to water-related hazards be manifest by 2050? So this has a place dimension, this has an exposure pathways dimension, and it obviously then calls upon us to look at the science that is needed to define what this means, both in terms of human dynamics, climate dynamics, and water dynamics. So that's the overarching sort of idea that I'm trying to put forward. Within that, some of the framing questions are, why and how are the renewable supplies of water distributed as they are, and how did this change over the planetary history? So this recognizes that if I'm going to look forward, I have to see whether the science that I have developed as a community is able to adequately explain some of the things that have happened in the past. So these are changes over long periods of time, because the argument is that those changes represent a significant departure perhaps from the climate, the land use, and other factors that exist in terms of hydrology as we know it at any scale that we are interested in on the planet today. So we have to look at this as a starting framing question. The second one is, how does water determine climate, vegetation, human presence, and economic activity? And correspondingly, how does climate determine water, vegetation, and human activity? So these are very basic questions with space and time dimensions, looking over time scales that are perhaps from centuries to millennia. And perhaps some of you know the answer to all this, and I think in a popular sense we probably do, but the question that I'm asking is, what kind of precision can we give to our answers to these sort of questions? Particularly in a world that is being changed by man the whole time, right? So that brings us to the next framing question, which is, what is likely to change in the future, and what do we need to do to answer the central questions that were on the previous slide, which started out perhaps as management, technology, policy, behavior questions, but then translated into broader science questions. And specifically, this says, what are the risks that we should conceive, and then how could we manage them through technology, behavior, and policy? But clearly, to bring those three elements into play, we first have to develop an understanding and a predictive capacity with and without those technologies and behavior modifications in place. Okay, so this brings me back to thinking a little bit about what is hydrology. So obviously one goes to Wikipedia and you're told that it's the study of the movement, distribution, and quality of water on Earth and other planets, including the hydrological cycle, water resources, and environmental watershed sustainability. So whoever wrote this did a pretty good job, because in effect it captures that the field we are in is a robust, and diverse applied science, but with a terrestrial focus and with links to many disciplines, and with studies that typically focuses, or so far has dominantly focused on the micro scale, pore spaces, for example, to hill slopes to river basins. And indeed, there is a growing literature on global hydrology. So, and since that's what I'm trying to argue is an important part of the story that we have to develop, that's not what I've listed here as a dominant feature at the present time. So, as I thought about this from the larger perspective or a more fundamental perspective, I wondered if hydrologists such as me could answer some of the questions that I get asked when I go and talk to K through 12 classes or to people who are not hydrologists. And so I've got some of them out here just for you to think about, because they reflect on how other people think about what we do in our field. So the first one is, how did water get here in the first place? And why is there so much of it? So I would like to know what people think about that. And as I go through these questions, I would also like to know whether people think these should be in the first few chapters of a hydrology textbook and getting taught in beyond K through 12. The second one is, what are the determinants of the chemical and biological constitution of water at any place of interest? So this is not the reporting of it, but how does that chemistry evolve? And I know that there's a good number of people who can answer this kind of a question. Third one is, why in aqueous media do like-charged substances actually attract one another when it is expected that they will repel each other? This one was very interesting because a person who was working on an Intel Science Talent asked me this question, and I was frankly surprised. I was not aware that there was any literature of that sort. In fact, I don't think this is the way we model things in our field, so I'm throwing that out. And then the next one is, why is water essential for the origin and maintenance of life? Good question. I don't think I had a clue as to how to answer that other than saying that it is. Finally, how do people use water? Who uses water for what? And why is it that they are not able to reuse it at a very much larger scale than they do today? And what would be involved in doing that, and what would be the hazards? So that's the first set. And I'm going to keep throwing questions or ideas at you and eventually show you some pictures so that you're not bored to tears. So one of the things that I wanted to do, and when I gave a talk at EGU a few weeks ago, I was asking the question as to what would it take to have parents tell their children that they would like them to be hydrologists rather than doctors, lawyers, engineers, or movie stars. And I think this set of questions perhaps goes in that sense, and we are jumping very quickly to a global aspect. And the question I'm asking is in the following way: how does water actually shape our planetary future rather than the other way around? And so when you think about it, some of these questions perhaps will be thought of as climate questions or questions that meteorologists or oceanographers or others should answer, but I think they need to be really at the heart of what we also talk about when we talk about water. So if you look at the biggest uncertainties in the projection of future climate change, those go to clouds and the regulation of climate. So perhaps you think of that as a radiation problem, perhaps you think of that as a scale problem in climate dynamics, but unless we resolve that, I think much of what is being said about what will happen to the hydrology of the future cannot be said with any confidence. Related to that is the organization of the water transport in the atmosphere. This has become pretty clear in the recent decades through things such as atmospheric rivers, but it's broader than that. And I would argue this is another thing that hydrologists really need to understand in terms of being able to say something about how the planet really depends on water. Obviously, the form, intensity, frequency, and quality of precipitation and where it happens. One of the major issues with CO2 enrichment of the atmosphere is that it will translate into CO2 enrichment of the oceans and the lakes. And so that's another issue that we have to think about in terms of planetary regulation. Changes in vegetation, associated water energy balance, obviously. And finally, something that is closer to the terrestrial side, being driven also by the vegetation changes, is the space-time availability and quality of water. And here I'm talking about the availability to man and to life through the typical water bodies, and how this determines regional economics, human migration, food, energy production, and land use. If you look at the literature, you will find, for example, that in America, we have determined what the value of energy is to the American economy. There is not a parallel and equally compelling argument made for water, and it needs to be made. Okay, so now coming to the future and where we are. So the way I'm framing that is in a statistical context. So if you have a certain body of knowledge and you want to develop an additional piece of knowledge, and there are competing things that you could do, the way you assess that in our models typically is we look for, if I have a unit investment in additional data collection, for example, what would be the marginal value of incremental information from the different pathways that I could take? And then I would like to take the one that has hopefully the highest marginal value of information. So that's what I'm talking about here. So we usually look at climate, which is precipitation, wind, radiation, humidity, etc., as an external boundary condition for hydrologic models. Similarly, we look at human water use, diversions, pollutant loadings, etc., as external forcing in our models. And we've done a lot of research to parameterize our hydrological processes, while the factors I listed above are external. And surely much more needs to be done there. But then I asked the question that if we want to answer the driving questions I posed earlier, then is it likely that we would gain more from investment in further improvement in the parameterization of existing hydrological models and flow pathways? This is what the other two debaters have focused on, respectively, on flow pathways and parameterization, or improving our understanding of the drivers of the watershed hydrology and bringing them into our knowledge base rather than having them be external. So that's the question. And so now I'll start with connecting one water, one world, and the many climes aspects. And this is the climate piece coming in. So the point here is that the oceans and the atmosphere are major carriers of water in an organized way and prescribe the space-time distribution of terrestrial water, whether it's in rivers, vegetation, lakes, and so forth. And yes, there's feedback from the terrestrial part and reorganization of these fluxes, and those are important areas to look at. So here the question that I asked in light of the previous slide is that if you model river flow, floods, or other related processes in a natural system, how much of the variance of the state variable that you are interested in, whether it's the peak flow, whether it is the flow in a given month, whether it is groundwater discharge over a 1 year or a 10-year period, or its contaminant transport, is explained by the larger scale processes, and how much is repartitioning locally. This is the way to frame the marginal value of information question. And what it also says is that depending on your purpose, the answer will be quite different. Okay, so to show you some pictures now and get you away from just looking at boring text, here's a paper by Van der End and Hubert Savinage, and it's similar to several other papers that are trying to do this kind of thing now. And what these people did is that they look at ocean sources of continental precipitation, and they have marked those out as the major sources in different colors there. And they number these regions, and they try to look at where this water goes and where the water is predominantly coming from continental sources. But keep in mind that the continental sources of evaporation that lead to precipitation in continental sources usually, depending on the season, are initially stimulated by precipitation that came from the oceans and more typically from tropical oceans in most places. What I found interesting, and one of my students pointed this out as an interesting quote from this paper, is they say that in this paper we have stressed the fact that all water that evaporates eventually precipitates, hydrological cycle from kindergarten. But they say in hydrology, this idea is not mainstream. Evaporation is a loss and precipitation is an external forcing. I have never really absorbed that hydrological principle, so I was a little surprised by that statement, but nevertheless, I think it is reflective of where we are. So if you now come to another paper, this was interesting because these people talk about aerial rivers and lakes, and they are showing that on the left. So they are showing that this river is essentially a large-scale atmospheric moisture transport that in the cartoon is during the wet season, and it's regulated by convection that occurs over the Atlantic and by the Andes, which form a physical guide to the system. And then they show the area over Amazonia as an aerial lake. Now, the interesting thing with these things is that the fluxes that we see in these atmospheric transports, which are quite organized and focused, is typically substantially greater than what we see in terrestrial rivers, and yet they are organized. So that's kind of interesting. On the right-hand side, in the top two graphics, they show in the wet season what the moisture transport looks like in November through March, and then April through July. Then in the dry season, they show that the moisture transport is quite different. And then they show you the correlations in each of these seasons between precipitation and those moisture transport factors. So that is nice because it shows you where the precip comes from and that it's associated with these things. And we have done work in the same geographies looking at floods that have happened in different places. And indeed, when this particular moisture transport pathway is very active, different places along the path at different times of the season will receive excessive precipitation and floods. So that brings me to this arc storm idea that Mike Dettinger and others at the US Geological Survey have been talking about. So this is very much the story of what atmospheric rivers can do. And these people had dug up an event from 1861-62, which was significant because there were waves of moisture that kept on coming in along these atmospheric river pathways, and it essentially inundated a very large area in central California. And what's interesting is that this phenomena has been now established as something that perhaps happens on average once every 200 years based on sediment chronologies in these areas, and it's spectacular. So in our work, we have this was some work that was done by one of the postdocs working with me, Hyun Kwan, about 10 years ago, and we started looking at whether these kind of features from atmospheric rivers or tropical moisture exports were significant in terms of floods in the United States. So all the blue dots that you see here are, this plot is off because it's plotting them in the ocean, so it's shifted out a little bit. But basically, these are all locations at which 10-year or larger flood events were recorded between the year 1910 and now, and 2005. And the arrows show you atmospheric moisture transport averaged across the 5 days preceding the peak of the flood and what was going on globally. So obviously, there's transport happening in other places also, but you see that there's significant transport associated with the flood zones. And this was done for different locations in the United States, and what you see is basically the same phenomena happens in all the different places. So this was phenomenological. And then another student I've had, Jenny Nakamura, who has worked on this, looked at the Ohio River, and what you're seeing here is an average across 21 different events that were 10-year events or larger. And she looks at the atmospheric transport that is associated with those events. And the anomaly from the average on those calendar days. And what you basically, and this the one below is a particular event, and what you see is that even average over all these events, similar to what I showed you in the previous slide, these things are quite coherent. One interesting thing that she found as she did this was that when you averaged across these events, and that's the line shown in black, and the grays are the spread across the 21 events, those the precipitation patterns associated with that are quite coherent, and in red is the April 2011 flood event, which was significant, and you can see the same sort of thing happens there, that there are synoptic waves of moisture that come in every 4 to 7 days with a fairly strong amplitude, And so as a hydrologist, you would say, okay, those are the things that are feeding my antecedent condition, and then there's where the flood comes in. But the point is that these are all part of a wave train that originates from roughly the same place and ends up in roughly the same place as well. So it's interesting to see that there is that sort of connectivity between the land surface hydrology and the atmospheric wave trains that we are talking about. So similarly, another student, this is Meng-Shon Liu, she's looked at transport coming from 4 places in the tropical oceans to different places in the world. This is Western France for a big flood in 1995. And the trajectories associated with that flood for different days preceding the flood event are shown on the left. And you can see there is coherent transport and then moisture release in this area. And what she did that was interesting was she looked at sea level pressure daily patterns in the 40 to 60 degree north band only, did a principal components analysis, and then did a simple regression versus rainfall in all the years excluding this big 100-year event. And then she uses that relationship to try to predict what happens in that year and does quite well. Explains about 53% of the variance only using the sea level pressure. So the circulation pattern is sufficient to explain what happens in terms of extreme precipitation in this event as you go through. So these are things that are interesting. Here's some work she's done in the Northeast in a similar vein, and the big story here is that the moisture release associated with these tracks is when the rainfall exceeds the 99th percentile is the probability distribution in blue, and in red is the probability distribution of moisture release from the tracks when it is less than that. So it conclusively establishes that this large-scale moisture transport is responsible for what goes on. And in the Northeast, she finds that this kind of mechanism is active all year long. Okay, so the main observations here are that given these aspects of climate, what we need to better understand as hydrologists are what are the sources of persistent organization of atmospheric moisture transport from the tropics, including their association to deep convection? What controls the moisture convergence into the areas that flood? And frankly, it doesn't have to be a flood. Just in terms of the delivery mechanism, these are the things that are important usually. Then there's been quite a bit of discussion in hydrology about scaling, area scaling in floods. And what we have found in a paper that we are just submitting is the duration of flooding also scales in a very interesting way across the globe. And there may be possible relationships of that to scaling in tropical convection durations. So these are things that start tying the hydrological cycle across the world together for us, which in an interesting way. And the question that comes is, okay, it's fine that you show all of these things, but looking at different geographies, different seasons, and different underlying climate states, can you predict these things? And if you can, then that would be quite interesting, right? So I'm moving now to the last segment of the presentation, which is bringing in the many souls part. So this is the idea that many people have started looking at now, and it's being called the Anthropocene, it's being called hydromorphology, it's being called social hydrology, depending on the bias or the context associated with the investigator. But the main part is that the human role is being acknowledged and being understood. So let's start with that, which is on the left, on the Anthropocene. And the questions are, how is human activity modifying climate? How is human activity modifying water bodies? How is water use determined by economics, land use, etc.? How will improved water use efficiency impact the local water balance? How do hotspots, such as urbanization or in large-scale intensive agriculture, change water fluxes? So these are the type of questions one set of people looks at. The hydromorphology people are similar, with the difference that they look at evolution rather than simply structural change and the attribution of that change, which is what the Anthropocene types like to do. So in the evolution, this is now looking at feedbacks and in space and time. That's the main sort of difference. And then the things that are of interest are if there are emergent patterns in space and time associated with these evolutions. And in the human context, there's the last bullet that I have there, which is we should think about water infrastructure and its evolution in time and space as a response to population and climate dynamics. And then we can look at how that major modifier of water fluxes on land in turn influences water and climate future. So some of these ideas I'll develop out here. And again, tying into the climate, one of the things that people are starting to talk about is the hydrological cycle accelerating or decelerating. So this is a paper by Sun, Farquhar, and Roderick. And they present some information which suggests that contrary to the very popular pitch that as the CO2 increases and the planet warms, we'll get an acceleration of the water cycle, the evidence is not quite there. And they attribute that to the presence of aerosols, which are not as well mixed around the globe as CO2. So where aerosols are dominant, you get an effect that is of a dampening of the hydrological cycle. Precipitation is perhaps reduced and its variability is also reduced, whereas elsewhere something else goes on. So these are both human factors that go in, and of course there are other factors, but these people highlight these two for now. So we have a debate at the largest scale for these particular attributors. So when I saw that paper, which is a 2013 paper or 2012 paper, I was reminded of an analysis that one of the people, Asif, working with me, did in 2002. We did a global average of precipitation and temperature, and we did a phase plot associated with that. And to reduce noise, we smoothed it by a 10-year moving window. And what we observed was that indeed between 1900 and 1976, you have an increase in precipitation as temperature goes up. But since then, we actually had temperature increase, but precipitation was going down. And this was globally averaged over land, which was kind of interesting. And it seems that the work that Sun et al. Are doing is confirming those kind of patterns, but they have the added dimension of looking at it decadally. So at the largest scale, we have an uncertainty as to how the system functions with regard to water, is the message that comes out of it. Then I wanted to actually develop more the human story. So this particular graphic looks at pathways of river basin development that we have seen. And they range from, on the left, low intensity development, primitive people, to higher intensity development, which really supports a much higher food production and population growth as a result, and reduction in poverty. But what you can see is that if you increase the intensification sufficiently, the water constraint can kick in strongly, and you could end up with either a collapse of the system or cycling back and forth between these things. And it's quite unclear as to how this could map out. And this is, I'm posing this not as a postulate, but something that needs to be understood and studied. And one of the observations of this that we see is that there has been self-organization in where people have ended up living over the centuries, rivers and coasts, because of the access to water, both for use as well as for transportation determines that. But in the 20th century and in the 21st century, we saw that some of this pattern was distorted to areas that are dry because deep aquifers became accessible as energy was available, stimulating changes. So trying to understand some of this becomes interesting. So I'm going to walk you through a quick story here. This is a paper by Will Steffen and others who look at how land use has changed and how that has affected water vapor over the 20th century. So basically what they do is that they look at changes because of deforestation, which are shown here in terms of water vapor, and changes due to irrigation, which are shown here, and the combined effect. So the interesting part here is that most of these things are predominant in India and China, and then in parts of the United States and here. So it's not, in that sense, a major global story, but you can think of it as a hotspot story. So the question is, can we look at some of this part and see what goes on? So one of the interesting things that comes up here is from North India, and the same story is true in China, that there is, this is in a very rural setting, and what you see is that there's a significant emission of dust and smoke from people burning crop residues. And this is a very large-scale phenomena in these areas. This is another paper which talks about that and what has happened. And the story here is that essentially you have very high-density rural population now, which has led to increased biomass burning and a decrease in NDVI as a result. And the net effect that people are speculating with respect to this is that that changes the radiation balance and also the atmospheric composition in the pre-monsoon season, leading to changes in the timing of the Indian monsoon, as well as changes in the intensity of the East Asian monsoon. So this is what I was talking about right in the beginning as to far-field effects from human activities in one place which change the coursing of the system. Now, the activity that we were just looking at can be also couched in the sense of what people are talking about, which is can we feed 9 billion people in 2050? So let's look a bit at that, and this graphic tries to show that there are two main stories that come out of this graphic. The first one is that in the developed countries or in countries that have improved their productivity with agriculture substantially, the yields for each of the crops that they were able to successfully improve have plateaued out, so that there is not as much scope for improvement in those locations. This improvement has come to a great extent by applying irrigation, a factor of 2 gains in terms of means sometimes, and a dramatic gain that you see in the bottom slide in terms of reducing the coefficient of variation of yields, which is very important in terms of sustainability and resilience. So the question that I ask given that story is that, okay, we probably are looking at having to grow large quantities of food as we move to larger population, but we are also going to have to provide them with the energy and minerals which support the production of energy and other activities. Where is the water going to come from? And where are the places where you're going to be realistically able to do this? So here, if we look at what has happened in the Indian context, where the transition has been successful in moving from a population of 400 million to 1.2 billion, and overcoming a food constraint, so to speak, the thing that has happened is essentially a crash of groundwater that's been taken out to meet the food growing objectives. And if we look at the US, what we see is a similar trend where the groundwater use as a percentage of the overall use has increased over time, and you see the map here which shows the intensity of that. But corresponding to that, in the US, the interesting thing is that if you look at the right graph on the top, the total irrigation water that we have been applying has actually been going down over time, even though the cost of this has been going up because of energy cost increases in real dollars. And this has been accomplished by shifts in 2 things. One is the mode of irrigation, which is shown here on the bottom right, and the second is by shifts in the crops that are being grown. So those are the factors. And the question is that, is this something that is likely to erupt worldwide? Both these transitions, what are the factors that will allow them to happen? What are the factors that will limit them from happening? And so if we look, this slide again basically informs us that what started happening over the world was that food was becoming plentiful because of the productivity increases that came with the Green Revolution. So one of the big factors there was irrigation. The other is obviously fertilizer, but that's a big factor. And the paper that is cited here, which is an FAO and World Bank document, basically points out that unless there are dramatic increases in water productivity or major shifts in the production patterns to more dryland crops and the rice wheat sort of things that have evolved over the 20th century, we are looking at close to a doubling of irrigation water use by 2050. And what's the prospects that you're going to be able to do this? Here it reaffirms that the areas where you could probably get the biggest productivity gains or areas with the lowest productivity, which sounds like a good story because the areas of the lowest productivity are also the poorest parts of the world. So if the richer parts of the world, for example China at this point, were interested in improving productivity in those countries, that may be mutually beneficial, but then overall you still have to look at what it does for water. So as I said, this is a groundwater story to a great extent in terms of irrigated agriculture. And this graphic shows that that comes with very high energy inputs in some of these areas which are traditionally arid. And the rice is the interesting story here because 40% of global irrigation water goes just for rice. And in places where groundwater is used, it increases the energy intensity in agriculture by a factor of 30. But what we found from our work in India was that it's possible to reduce the application of water for irrigating rice, for example, by 30 to 40% with very little capital investment. And so the potential is high, but unfortunately the arguments for how and why we need to do this are still not coming across as compelling. Okay, so moving from the rural thing to coming to urban things, another point I wanted to make was our connection with the human use is very interesting. So the first graph that I'm showing you is for projections that were made at different times in New York City. The population growth in New York is shown in the green curve, and the water demand is interestingly in the blue curve. And what you see is that we are remarkably lower than where we were in the 1970s and 1980s, thanks to specific efforts that were made by New York City. But look at what the predictions were of water use and what they continue to be, and they are quite at odds with what the actual trends seem to be. Similarly, here are projections for Washington, D.C. made at different times by different groups. And what you see is that, again, the population trend goes up, and most of these water use projections seem to mimic the population trend, and the water use is actually lagging those significantly. So just at that very basic level, I found it interesting that we need to develop an understanding of what the factors are that lead to use, what really is the competition between different human activities, how it can get managed, and what that would mean for water resources. So summarizing this, the main observations that I have for this section are that coming from the soul's direction or the human direction, agriculture, urbanization, globalization, and energy production are the major water use drivers locally and globally. All of these are likely to shift dramatically by 2050 as they are constrained by water and climate. In turn, these will affect land use and climate. What is our ability to conceptualize and do something reasonable with this beyond the kind of things that are being done in the unidirectional climate change, IPCC style projections, and then downscaling, bias correction, use kind of scenarios which are not particularly informed by how humans are likely to react to some of these changes and how adaptation might proceed. Second, the prediction of water demand and use and of infrastructure development and its impacts seems to be very poorly constrained and has possibilities for innovation that will map eventually to more efficient and equitable use. Last, the controls on those things are pricing and technology controls. There are many innovative technologies that could stimulate massive reuse of water in urban settings particularly, but the pricing structures do not allow large-scale development of these things. And the context in that is that imagine a world in which you had highly distributed smart grids for urban water storage, rainwater capture at different locations, for example, point-of-use treatment and reuse at a massive scale. What would that do to our future water trajectory in these hotspots that are out there? And I think this is something we need to think about and shape. Okay, so summarizing, the points that I have are back to how can we assure a reliable supply of water of appropriate quality for all life around the world by 2050 as the driving question. And in my view, this opens up a vista of interdisciplinary inquiry into areas that are key to planetary sustainability and the resilience of life. That would really raise the profile of our field if we were to follow that sort of an articulation. And this is not separate from traditional hydrology. You obviously have very strong utility for traditional hydrology mapped to this particular context. But what it also does is it leads to the emergence of hydromorphology as a science, which reflects the interlinked dynamics of the drivers of hydrology and focuses on the emergence of pattern and form to inform prediction and management. So that's my pitch, and I'll stop and see what people think.
Well, thank you very much, Manu. I hope others, share my appreciation for this talk. I find it quite inspirational and very interesting way of kind of posing where we are. We do have some questions coming in, and so I'll also just tell everybody to please put questions in the chat box. Alberto's asked me to sort of help moderate this part. We have we're at the top of the hour, but let's keep going for another 10 minutes or so if there are questions. So we have one question from Magdalena Muir. Given important role of groundwater and also links between energy and water, can you please comment on links between groundwater and renewable energy, and also the role that desalination can play in meeting water needs and replenishing groundwater?
Yeah, so let me start in reverse order. I'm going to take desalination as a code word for innovative technologies that can purify water with any chemical or biological concentration to a desired level of usability with, so let's say that's the definition that I'm going to use. So the idea there is that what I think is emerging on the technology frontier there are technologies using forward desalination, using nanomembranes or nanofiltration technologies and other things that promise to dramatically change the cost structure and the energy intensity of being able to do that. And likewise, we are seeing advances in sensor technologies that will allow us to, in real time, at least pinpoint the key indicators of water quality so that it makes it possible for a user to conceive of having essentially a small box sitting in their kitchen that creates this water and shows you exactly what the water quality of concern is. So I think there's really a major change that can come in that direction. But the caveat on that I'll put is that some people start thinking in the sense of we'll do large-scale desalination and then do agriculture. That's interesting, could happen, but particularly with brackish waters. But I think a more likely scenario there is that we will end up with technologies that allow us to grow crops in brackish waters directly through genetic modification. So it'll be interesting to see how those two things compete with each other. Now, groundwater and renewable energy is an interesting one too. The two renewables that are applicable here are solar and wind, perhaps, is what Magdalena is thinking. So the challenge here is that if you go with solar, the land area that you would have to cover if you use PV would be quite large if the depth to groundwater is large. So then there's a trade-off between crop versus solar. But if you look at concentrators or if you look at solar thermal technologies for energy conversion and do cogen with that, then this becomes fairly competitive with wind. The main issues with both of those are the intermittence associated with the supply, but this may be actually not a bad thing in this particular application because one can conceive that the groundwater that is pumped up could be stored somewhere and then used, or there is a way to apply it such that with sensors, there's an application scenario in which you're maintaining soil moisture at optimum levels, approximately, within a window, and not having to worry about the exact time of application. So those are the two answers to those two, and I'm happy to respond more.
Okay, so let me go to a point of clarification from Fuxia. So we were wondering if the values you showed, this concerning decrease in demand for water in New York and D.C., if those values include virtual water, if they're strictly municipal demand. Let's just answer that question first.
They are strictly municipal demand.
Okay, that's probably what I assumed. Okay. Our thought was that perhaps as density increased in these cities, water-intensive activities were displaced, i.e. manufacturing exported outside of the city limits.
Sure. It's a combination of those things as well as explicit conservation measures.
Okay, very good. Then Todd Rasmussen has a question. Given this framework, how would you approach the Egypt-Ethiopia dispute on the Blue Nile?
That's a really interesting question because there are two elements to it. One is the climate element because that now brings up the fact that there's interannual variability that is structured on the Nile. There's decadal variability and perhaps multi-decadal variability, all of which people speculate have some predictable structure or at least the ability to model in a stochastic sense so that you could define the regimes. And the reason I'm starting with that is that as we have learned with the Colorado River project, if you take any finite period of record and try to allocate the resource in some deterministic way between the parties, you will fail, because you will have wet periods and dry periods that are quite a bit out of the norm for whatever period you used for setting the benchmark. So I think that is one of the first elements that has to be brought in, and once that is in and there's transparency as to that, the story that emerges in terms of how one can manage this is one that can be mapped very quickly into a cooperation story. Egypt has the highest productivity of agriculture grain in the world, roughly 10 tons per hectare on rice. Ethiopia is one of the lowest at the moment. So, and Ethiopia also needs the hydraulic energy that could be generated by this. So you can conceive of a situation where there is a trade agreement that goes beyond purely water and the operation of the system, which is important to look at, but it sets up a mechanism by which the hunger aspects in Ethiopia are dealt with by a transaction from Egypt on food, and there is joint regulation of the flows, recognizing the different timescales of variability, so that there is an optimum outcome for both groups. So that's what I would visualize in that particular case.
Okay, thanks. Let me there's about two more questions here, probably we'll have to wrap it up. So one, Pete Laus is asking, hydromorphology seems to me to imply people are not an important part or driver of how we characterize or manage water. Any reaction? And I'll just stick in here.
Yeah, no,
this goes back to this problem with this word.
Integral to the hydromorphology story. In fact, that's what I was trying to convey. So I'm sorry I failed completely in getting that across.
Yeah, I'll just go back to this is the argument I've had with Vogel all the time over this, is that this word, just people glom onto what they think it means, and I know you guys think it's a very elegant term, but oh well, be that as it may. So Cesar 2 asks, talking about density, I think we're going back to the urban question, and about urban sprawl. Is there, from a water perspective, a more sustainable approach, presumably, to urban development?
Yeah, so, I don't know what Cesar is thinking, but there are two aspects. One is on water use. The second is on wastewater treatment and stormwater disposal, because, all three are currently treated as three separate entities. You look at EPA, they have a drinking water program, they have a wastewater program, and a stormwater program, and there are some connections between them, but not necessarily. So I think in the one water sort of paradigm, there is a possibility, because if you look at what people working on stormwater nowadays are talking about, their idea of green infrastructure is that they will do porous pavements to increase infiltration. They will do green roofs to capture water and evaporate it through plants or otherwise. And they talk about increasing wetlands to increase the dissipation capability for stormwater without negative impacts. Suppose you change all that and you say that what you are interested in is actually capturing much of that water and using it, and then quite a bit of the wastewater that you are generating is then recycled and used at the point of use. So a few back-of-the-envelope calculations suggest that you could get to 60 to 80% recycling of water. You could capture a certain amount of water on roofs so it is not contaminated by flow on streets which are likely to be dirtier. You could do a bit of first flush and then translate that into local storages and then local treatment and reuse. So if you do this, it's conceivable that you can cut down current intensity of use and the stormwater aspects and the wastewater aspects significantly. The economics of this have to be worked out, and the ick factor aspects of this have to be worked out. But I think unless we articulate those, the technology development will not take place to get there.
Okay. Let me just take the last two questions we have in the chat box. So let me first start with maybe a slightly narrow one. How do water issues in California and LA in particular relate to the conclusions made on New York's water use? Have you looked at that?
Okay, so what's interesting in California and LA is that they are actually at a very different level of stress and import than New York is. What people perhaps don't understand that is that New York City actually imports almost all its water from an external watershed. So in that sense, there's a similarity with California. But in terms of the demand to supply ratio, even after the import, there's a huge difference. In terms of California and LA, people seem to be still going much more heavily in the direction of desalination and looking at imports than they are with reuse. And that is similar to what is happening in the New York metropolitan area as well. Some people are looking at desalination even though we are surplus. And I think the projections of future water use in California and LA are likely to be similarly flawed, because as the cost structure of these things changes, the consumption patterns are going to change dramatically.
Right. Okay, then finally, the last question is a follow-up from Magdalena. Given the interconnectedness of energy, water, and climate issues, to what extent should there be a focus on improving water efficiencies and avoiding water losses across all water systems? Very high rates of loss.
Absolutely. You know, the thing here is it's a pricing issue, because it turns out that in the analyses done in New York and Boston and DC and Philly, what people determined was that at the current economic level at which water is put, what is being charged for water specifically, it was uneconomical for these people to try to reduce losses beyond 25%. So many of the people in the water industry are pushing what they are calling value of water initiative, and they're trying to make people recognize that the value of water is not simply what you're paying for it, but the externality value as well. And if you account for all of those things, then it's important to do this.
Okay, I think with that we probably should wrap it up. We're approaching 15 past the hour. Any last comments from you, Alberto?
My only comment is that I really enjoyed this discussion, and I was really amazed by the number of questions. And I tell you, I had the intention to ask a question myself, but I think I was really impressed by the significance and the deep concepts that were already discussed. So I think it's just enough if I really express my appreciation for this initiative and my appreciation for this discussion. I will tell my students to look at this conference offline. I think it has been really interesting.
Very good. And it is being recorded. I know, Emily, if you can bring that initial slide back up again. So the next installment in the series with Jeff McDonald and Keith Bevan will be in June. I don't remember the date exactly, but it's coming up on your screen right now. Will be June 24th, again at the same time, 9 a.m. Pacific across till 6 p.m. Central European time, and we encourage you all to join us. Thank you, everybody, for joining us, and really appreciate it. Thanks, Manu, for the time. I think it was a great talk and quite inspirational.
Thanks very much.
Talk to everybody later. Bye-bye.
Bye.
Bye.